Good afternoon. Let's start the afternoon session. Welcome. And we'll have three talks. And the first talk by Charles Fefferman, formation of singularities in fluid interfaces.
So thanks. It's a great pleasure to be here. Happy birthday to Sinai. Happy birthday to Ruelle. Happy birthday to Beethoven. The last is actually not clear, but I think it's even more accurate than the previous two statements. Beethoven was baptized on December 17th, 1770. Before. Yes.
Beethoven is today.
Well, Beethoven. All right. It depends on whom you talk to. I'm sorry. Oh, the microphone is. The microphone is in the wrong place. How's that? Okay. All right. Now, all right. So this is going to be an expository talk. This is not for the experts in fluid mechanics. The experts have heard it all before. All right. I'm going to be talking about problems in the fluid mechanics of incompressible fluids. Compressible fluids have lots of singularities. That has been known for a long time. But incompressible fluids, well, probably have singularities too, but that is much harder to prove. Until rather recently, I believe no physically reasonable incompressible fluid equations were rigorously known to have any singularities. But a few years ago, several Spanish friends and I investigated a couple of these equations, and we found two examples of incompressible fluids with interfaces in which the interfaces form singularities. So I'd like to talk about three problems. Two of them we have rigorous results for, and one we have only numerical simulations, but the numerical simulations show something promising. Okay, let's see how techno-challenged I really am. So there are the slides. Okay, formation of singularities. So again, I'm going to discuss three problems about incompressible fluids with boundaries, that is interfaces. The equations are the water wave equation, the Muskat equation, and something called the alpha patch equation, and singularities form. That's the punchline. Okay, here are the teams. So for water waves, there are the people who did the work. For the Muskat equation, there were the people who did the work. And for alpha patches, there are the people who were involved in the simulation and its analysis. Okay, and here are the papers. So there's one, another, and a third. Okay, now this is an expository talk. I'm not even going to state precise theorems. I'll just give intuitive ideas and vague statements. I promise you there are precise statements and correct proofs, and if you go to the papers that I put on the screen, I promise you that correct details are there. Okay. So here's the plan. I'm going to state the problems, and I'm also going to summarize the proofs of one of the two breakdown results, the one for the Muskat equation. Okay, so the first problem that I want to talk about is the water wave problem. So let's say we're in two dimensions, and the world is separated into vacuum above an interface. Here, let's see. There's a vacuum. Here's the interface, and here this region is filled with water. Now the water at a given, the water region at time t is omega of t, and in the water region, the velocity of the water at position x and time t is u of xt, and the pressure is p of xt. And let's say the water is subject to gravity. So the forces acting on the water are gravity, and whatever forces result from the pressure, and that's it, we ignore all other forces. Okay, so in particular, the velocity is a vector in R2, the pressure is a scalar, and they are defined only in the water region. X is in omega of t. And of course, we don't know what omega of t is, so part of the problem is to find the time-varying region. Where is the water? Okay, now in order to write down formulas, let's represent the interface, so the boundary of the water region. Let's write it as a parametrized curve as in the slide. So z of alpha t is a point on the interface at time t corresponding to a parameter value alpha. Now how is the curve parametrized? I don't know and I don't care. The parametrization of the curve has no physical significance, and so any convenient parametrization will be as good as any other.
So it's single-valued function.
I'm sorry, it's a single-valued function, yes. Okay, so this z of, so alpha is a real number, t is a time, it's a real number, z of alpha t is a point in the plane. And this is supposed to be a simple closed curve. Or a periodic curve, or a whatever, we'll see, okay? So that's the interface. All right, now what are the equations that we're solving? Well, in omega of t, the fluid is supposed to satisfy the 2D incompressible irrotational Euler equations. Now, the Euler equations are very natural. They just say F equals ma. The left-hand side is the ma. The right-hand side, let's see, left-hand side of what? This left-hand side is ma. Okay, u is the velocity. Du by dt is the time derivative of the velocity provided we sit at a fixed position in space, but a molecule doesn't sit at a fixed position in space, it moves. And so if we color one molecule red and we look at the time derivative of the velocity of the red molecule, then this is its acceleration. And then these are the forces acting. Here's minus the gradient of a pressure, and here's a term coming from gravity. So this is completely natural. This is F equals ma. If the fluid is incompressible, the divergence of u should be 0. It's not quite so natural to make the curl of u equal to 0. The curl of u might not be 0. But if the curl starts out being 0, then it will continue to be 0. And so this is merely the simplest case, the simplest equation to study, in which we do not need to worry about the effects of vorticity. Okay, so those are the equations. At the interface, the pressure, let's say, is 0. And furthermore, the interface moves with the fluid. At each point of the interface, there is a velocity for the water, and that vector field along the at each point of the interface, there is a velocity vector, and that set of velocity vectors carries along the interface. And so that equation is up here. Notice there's some completely arbitrary function c of alpha t here. It can be anything you like, because z of alpha t is parametrized in a way that we don't care about it. If you change the parametrization, you will change the c of alpha t, and picking an arbitrary c of alpha t is more or less equivalent to picking an arbitrary parametrization of the interface. Okay, so the equations on the previous slide were what happens inside the water region, and the equations on this slide tell us what happens to the interface and at the interface. So that's the problem. Well, all right. So notice we're taking into account pressure and gravity. Those were the right-hand sides of the F equals ma. I didn't include surface tension, but one can include surface tension, okay? And that doesn't affect the validity of the results. It makes the proof messier. Okay, so now we specify an initial interface, and we specify an initial velocity defined inside the initial water region. Initially, let's say the interface is nice and smooth, and the initial velocity is nice and smooth, and it had better be divergence-free and curl-free, so that as time goes on, the solution is divergence-free and curl-free. And so that's, those are the initial conditions. I just discussed the equations. And the question is now simply whether a singularity forms in finite time. Well, does a singularity form instantly? That's already a deep question. So I want to mention previous work. So here are some names, but in addition to the names, I want to make, in addition to just writing down the names, I'd like to make a few comments. So first of all, it was a big breakthrough when C.J. Wu in the late 90s found that for small time, the problem that I just mentioned is well posed in Sobolev spaces. So at least there is a solution for small time. If you look at the equations, they're really ghastly, and it is not at all easy to, I mean, it's the opposite of easy, to prove that for small time the solutions even exist. Well, all right, now that solutions exist for small time, what about large time? Well, there was a lot of work on small data. And let's see, the end of the story is that independently in 2013, Ionescu and Pusateri, and a little bit later, Alazar and Delors, proved that for small initial data, I won't explain exactly in which norm, but for small initial data, the water wave equation in 2 dimensions, that's a lot harder than 3 dimensions for this problem. The water wave equation has solutions for all time. Okay, so that takes care of small data. How about large data? Well, all right, before I talk about large data, let me mention also that in 3D there's global existence for small initial data, and that's actually easier than the 2D case. And also I mentioned that the restriction to irrotational flows is in order to provide us with the simplest problem, the simplest version of the problem. But in fact, for short time existence, one can also include rotation, and there are the people who did it. Okay, so what about large data? And so the first result, which I would like to state vaguely, is that in fact for large data, we can start out smooth and with apparently nothing wrong, but in finite time, a singularity will form. Beyond that time, no physically reasonable solution of the equation exists, and what's going on is physically completely obvious. It's the following. So there's the initial configuration. So the water region is colored some shade of green, and the vacuum region is above it. And so this is what happens at time 0. Notice that the interface is smooth. I didn't indicate what the initial velocity is, but it's also smooth. Okay? Now, we wait a while, and we are in this situation. The water wave has turned over at some later time. But the velocity and the interface are still smooth. However, you can see that trouble is coming. We have 2 waves, so to speak, and one is heading toward the other, and there's nothing to stop the collision. And so, at some later time, there is what we call a splash. The interface will self-intersect at a single point at some later time, but except for that one self-intersection, the velocity and boundary are otherwise smooth. So that's a splash singularity. Do you want to call that a singularity at all? I think it's reasonable to do so for the simple reason that after that, no physically reasonable solution of the water wave equation exists. The water does something, I don't claim to know what, but it doesn't satisfy the water wave equation. Okay?
But separation curve is not single-valued.
I'm sorry? Oh, so at the point where the singularity forms, the curve is not single-valued. Before that, it is single-valued. I'm sorry. It is single-valued. It is not one-to-one. I'm sorry. It is. The curve is. The curve. This can be This is a parametrized curve, so there's a single-valued function, but okay. It's not a simple closed curve. The curve self-intersects at one point. There's the picture. Think of how it's parametrized. Let's the parameter, as alpha increases, as the parameter increases, that happens. Pardon the shaking of my hand. There we go. Okay? So that's the situation. That's the singularity. Okay, here's a variant. It could happen that at the instant of collision, because of the special shape of the initial conditions, that we may find that the curve self-intersects along an arc rather than just a single point. So we call that a splat as opposed to a splash. Okay? So the water wave equation may start out completely smooth and free of singularities, and in finite time, a splash may form or a splat may form. Okay, now, is all that true? What can we prove? Well, we can rigorously prove that a water wave can start out as in picture A. Oh, Yasha, did you have a question?
I have a question to previous
Okay.
picture. So when you have this picture, is the separation curve defined uniquely, or you can erase this? There will be domain
Okay.
with the fluid.
Okay. What is? I guess. Okay. Mathematically, what happens is that for all times less than the time depicted there, the curves, it is a simple closed curve. But as time approaches the breakdown time, the picture approaches this picture. At the breakdown time, you can describe it as you will. You can leave the common arc in there. You can erase the common arc. If you erase the common arc, the fluid velocity will have a discontinuity. What will an actual fluid do? I don't claim to understand. Okay? But as far as the equations are concerned, for times strictly less than that, it's clear what's going on. And as time approaches a critical breakdown time, the picture approaches this one. And for times, if you want to go up to any time strictly greater than this time, there is no physically reasonable solution of the water wave equation.
But for this splat, you have you need many parameters, infinitely many, right?
Oh yes. So in the set, yes. So in the set of all reasonable initial conditions, this situation is of infinite codimension, but also of infinite dimension. Yes.
But you can have sort of higher order.
Oh yes, absolutely.
And then it's finite.
And then it's, yes, exactly. Okay, and any other questions? Okay, now.
Pressure is determined by the equation.
I'm sorry?
What about the pressure? You determine that.
And all right, let me think. The pressure is smooth up until the moment of
you don't specify it.
oh, no. It is specified by it is forced by the equations. Yeah. Okay, any other questions? Okay, so that's my assertion. Now, what can we actually prove? We can prove somewhat less, but, well, here's what we can rigorously prove. So the water wave can start as in A and then turn over as in B. If you remember the pictures A, B, and C, A was the completely reasonable thing that looked sort of like part of a sine curve. B was the turned over version of the wave, and so the wave can turn over and pass from A to B. We can prove that a water wave can start as in B with the two thingies headed toward each other, and then form a splash as in C or a splat as in C prime. We believe very strongly, but do not have a rigorous proof, that in fact what I said before was true, namely we have evidence that I'll describe in a minute, or that's described on the slide, that in fact you can start as in A and then continue to B and finally end up as in C or C prime. This is, the reason we believe this is that we have a numerical simulation. Now, there are many kinds of numerical simulations. The devil of a devil plaguing fluid mechanics is that whenever a singularity starts to form, almost by definition, that means that numerical simulations become unreliable. But ideas used in the proof of the rigorous stuff can be used to modify the known methods of numerics, in particular the method of Biel, Howe, and Lowengrub. The numerics can be modified in such a way that they remain reliable up to the formation of the singularity, which one sees in very easy ways. You know, you add more points, or you do the same calculation over again with two levels of approximation. And you see that they agree very well. It's quite clear that the simulation in the example that we have behaves the way I said, but we don't have a rigorous proof. On the other hand, as the last line of the slide points out, we're working to produce a rigorous computer-assisted proof. The idea is that we can try to prove a stability theorem with explicit constants that says that if you're given an approximate solution of the equation, then nearby there is an exact solution of the equation. And that would mean that if you have a sufficiently good numerical simulation that appears to show a splash or a splat, well, let's say just a splash, then close to it there will be an exact solution that forms a splash.
But there should be some assumptions
Oh yes, oh yes, oh yes.
on the approximate solution.
Okay,
Type of factor validity.
yes. So there's a laundry list of assumptions on the approximate solution, and what happens is that we hope to take the approximate solution that we as Javi, the approximate solution that we found, and check that it satisfies a whole lot of stuff, and then prove, also using the computer, but that's another story, that if a whole lot of stuff is true of the approximate solution, then near the approximate solution, there is an exact solution. That's the plan. But I don't claim that we have it. I claim that we do not have it. But we are hopeful that it can be done. Okay? Yes?
Is this equation time reversible?
Yes.
I'm considering if you can prove that there is a solution starting from B and a format.
That's what we do.
But what if I evolve solution backwards in time from B?
From B.
Yeah.
From B. Or from, wait, so you can run the solution forwards or backwards as you please, and to prove that you get from B to C, that is from that to that.
Yeah.
You start with that, you run time backwards, you get that.
Yeah. Then backwards again.
Backwards, yeah, all right. So that's plausible, but you have to prove it. Okay? Okay. All right. Any other questions? All right, let's see how I'm doing. Lots of time. All right. Okay. There's another proof that I want to mention by Coutan-Scholler with applications to three-dimensional water waves. But let me not talk about 3D water waves. However, let me say that one could ask how more realistic models of the behavior of fluids do or do not lead to splashes. What prevents a splash? Adding viscosity, for example, looking at the Navier-Stokes equation instead of the Euler equation, so adding viscosity to the fluid, by the way, that also affects the boundary conditions, never mind what they are, but there are natural boundary conditions for the Navier-Stokes version of this problem instead of the Euler version, and that does not stop the splash. That is mathematically interesting because you then cannot run time backwards. For the Euler equation, you can run time backwards, but for the Navier-Stokes equation, you had better run time forwards. Okay. Okay. What stops? So various things do not stop the splash. I mentioned that surface tension does not stop the splash. What stops the splash is an incompressible opposing fluid. Suppose that instead of water and vacuum, you have water and, I don't know, some other stuff, carbon tetrachloride, okay? And you consider that system. Then there's joint work of Alex Ionescu, Victor Lee, and me that shows that the opposing fluid pushes back and a splash does not form. That has to be interpreted very, very, very carefully. What exactly does a splash mean? A splash means that the interface self-intersects, let's say at one point, but absolutely nothing else goes wrong. And so what we prove is that if the interface self-intersects, something else is then also going wrong. So can the self-intersection actually take place? It's not known. Okay. Let me see whether I included anything else about this problem. No. Now, all right, now we forget about that for the moment and we talk about the next question. Yes?
What's the initial velocity condition like on the two peaks?
Oh, they're heading toward each other. Sure. Yeah. Okay. That's in picture B. In picture A, let's see, picture A. Javi, do you remember what does the initial velocity look like in picture A? Okay. 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 If your interest is such that you would actually like to get an email with some information about that, send me an email. I will forward it to Javi. Javi will answer it. I will forward it to you. Okay? Yeah, exactly. A, B, and C. Okay. Okay. Next problem. Okay. Next problem. All right. The next problem is called the Muskat equation. Muskat is the name of a person. Okay. The Muskat equation describes, for example, oil and water in sand. So oil and water are incompressible and they do not mix. And so there's a picture of oil, let's say above an interface in a region called omega oil of T, which varies with T. Below the interface is the water, and it occupies the region omega water of T, which again depends on T, and they share a common interface. Oil and water are incompressible and they do not mix. Okay? That's the setup. Now, okay, curiously, a completely different physical system is governed by exactly the same equation. I don't know why, but let me describe the system. It's called a Helly-Shaw cell. It consists of two parallel glass plates separated by a very thin layer of oil and water. So instead of placing the oil and water in sand, you place them between two parallel plates with a tiny separation. Helly-Shaw cells are often horizontal, but they can also be vertical. This one is vertical. And for some reason that I do not claim to understand, they're governed by this is governed by exactly the same equations as the other. Okay? So oil and water either in sand or in a Helly-Shaw cell. Okay, now, all right, at this point, when I give this talk, I always tell the same joke, and it's the following. Okay, let's see. In the particular translation of War and Peace that I happen to look at, there's the following wonderful sentence. Okay, we must seek to understand the laws of history, which govern the affairs of mankind as surely as the physical world is governed by force equals mass times velocity. Okay. Now, I have asked several Russian friends whether this occurs only in the translation or whether it actually occurs in Tolstoy, and I have gotten several interesting answers. Perhaps the most interesting answer is Tolstoy went to my university, and I bet it's in the original. Okay. Andrei Okunkov finally found what I think is the correct explanation, but I'm not going to disclose it. I leave it as an unsolved problem. Okay. However, F equals ma does not hold for oil and water in sand, and it does not hold for oil and water in the Helly-Shaw cell. What's with that? Well, of course, F equals ma in the real world, but you don't want to think about the forces exerted on or by the sand, and you don't want to think about the forces exerted on or by the glass. And so the net result of F equals ma or quantum mechanics or whatever is happening in the real world, the net result is that the fluids move according to an empirical law, Darcy's law. And Darcy's law is as described in Tolstoy, okay? The force is proportional to the velocity. And so there it is. You can see Darcy's law on the slide. One has to remember that the rho, the fluid density, is equal to the density of oil in the oil region and the density of water in the water region. This is a slight simplification of the full strength of Darcy's law because I'm assuming, let's see if I say this. No, I forgot to say it. When you have a fluid in sand, the fluid has a density and there is also a porosity, which is something or other about how the fluid interacts with the pores flows through the pores in the sand. I'm assuming here that the two fluids have the same density but different porosity. So when I say oil and water, I assume that oil and water are not actually like this, but never mind. So this is a special case of the full Muskat problem. All right. In any event, at the interface, of course, the interface is both the boundary of the water region and the boundary of the oil region. And again, I represent it as a parametrized curve, same as before. The velocity of the water region and the velocity of the oil region do not necessarily agree at the interface, but the difference between them is tangential. Otherwise, very strange things would happen. Okay? And let's see. And the pressure of the water in the water region is equal to the pressure for the oil region and in the, at the interface. And finally, the interface moves with the fluid, which is given by the set of equations at the bottom of the slide. And you can see that there's one version of how the fluid moves based on the velocity of the oil, and there's a different version of the velocity of how the interface moves based on the velocity of the water. And these two equations are consistent with each other. In fact, they say exactly the same thing. The fact that U oil and U water are not the same just tells you something about the difference between C sub oil and C sub water, which we're not going to care about. Okay? That's the problem. Okay, we're neglecting surface tension. And again, we restrict attention to the case in which the oil and the water have the, oh, did I say porosity? I should have said viscosity? Viscosity. Sorry. Okay. So now all right, we fix conditions at time 0 and we seek a solution for positive time. Okay. Now, unlike the situation of the water wave equation, here it makes a crucial difference whether the light fluid, the oil, is on top of the heavy fluid, the water, or vice versa. So if you look, for instance, there, the fluid with the smaller density is on top, okay, and the heavier fluid is underneath. That's good. That means if we try to solve the problem with time flowing forward, life is going to be good. On the other hand, if the water is on top of the oil, that's bad. What we should then be doing is solving for time going backwards, and then this would be good and this would be bad. However, if the fluid looks like this, we are seriously out of luck because locally over here the oil is on top of the water, and locally over here the water is on top of the oil. And so you cannot solve the problem locally with time flowing forward or with time flowing backward. Okay? So the configuration matters, and turnovers in particular look very bad. The Muskat equation in the good case, in the stable case, is a nonlinear version of something like the heat equation, except instead of the Laplacian, you use the square root of the Laplacian. Notice that then that's sort of that's a non-local version, a non-local, nonlinear version of a first-order PDE, sort of. Okay, so so in the good case, the model equation is that, and in the bad cases, we've got something like that with the wrong sign, and in the really bad case, we have something like the heat equation, but with this coefficient sigma that changes sign. Okay, so that's the character of the Muskat equation. Okay, here's some previous work on Muskat. So for small initial data in the stable regime, smooth solutions exist, and there are some of the people who proved results on that. In particular, this paper of Constantine, Cordoba, Gancedo, and Strain show that if the initial interface is the graph of a function, and if the derivative of that function, if the slope of the tangent to for that interface is strictly less than 1 everywhere, then global solutions exist for all time. So small data, even not so small data, have global solutions. But again, we will see that large data form a singularity. And so here's the nature of the singularity. So again, I'm going to show you pictures A, B, and C. So at time A, at time 0, we start as in figure A. The low density fluid is on top of the high density fluid as we would want it to. We're in the good case. It looks stable. And so it stays smooth for a while and life is swell. But later on, it turns over into the ghastly regime where we have no right to solve the equation either forwards or backwards. Nevertheless, a singularity does not form yet. The solution continues to be nice and smooth for a while, for reasons that I think will become clear later. So solution doesn't form yet, but at some later time we finally run out of luck, and at the origin, at the single point, a singularity forms. Now, what kind of singularity is it? Well, all the interfaces in question are real analytic. That's why we can continue to solve the equation once it's turned over. We have real analyticity. So equations that have no right to be solved can still be solved for a little while. But after a while, we run out of real analyticity. And in any neighborhood of this single point 0, the interface is C3 but not C4. Everywhere else at the breakdown time, the interface is real analytic. So in particular, the C infinity regularity, even the C4 regularity of the solution, just stops at finite time. It is very plausible, but as far as I know, not rigorously proven, that no reasonable solution of the Muskat equation happens beyond this time.
So it means that the fourth derivative is singular.
Yes, the fourth derivative is singular. Now remember, we don't care about the parametrization. So when I say that the fourth derivative is singular, what I mean is that this curve admits no parametrization with respect to which it is C4. It's not enough to show that the particular parametrization that we use fails to be C4.
But it's not a jump.
It's not a jump.
It's more complicated.
It's more complicated.
And there is no analytic continuation from both sides.
And there's no analytic continuation from both sides. Okay, so that's that's the nature of the singularity for the Muskat equation. All right, now let's see. I have not quite 20. I have a little more than 20 minutes left. A little more. Okay, let me quickly, very quickly. Oh, so all right, we have a rigorous proof of that. All right, let me skip quickly through alpha patches. In an alpha patch, you imagine that there is some simple closed curve that bounds a region omega of t. And there is some scalar, maybe it's a temperature or some scalar. Think of it as a temperature called theta. And theta is 1 inside the region and 0 outside the region. Now, from this temperature theta, we're going to form a velocity. This velocity is going to be incompressible, and therefore by elementary potential theory, it arises as the perpendicular gradient of a stream function. That means the perpendicular gradient is this thing. So psi is some scalar valued function. This guy is divergence free. And so this is just, the fact that u is given this way is just to say that it's incompressible. But then we have equations of motion. First of all, this theta is simply carried along by the velocity field u. And the velocity field u is produced from theta by this equation. We take theta, we apply to it some power of the Laplacian, and from that we get the stream function, psi. From the stream function we get u. So these are the equations. Alpha is a parameter. Okay. Special cases of this equation are interesting. Well, I claim the general case is interesting, but in particular, if you take alpha equals 0, you get a classical problem for the 2D Euler equation, so-called vortex patch problem. And experts in fluid mechanics know that this was thought to break down in finite time that was believed once upon a time based on numerical evidence, but in fact, the solutions remain smooth for all time. That is, the bounding curves remain smooth for all time, and that was proven by Chemin, and a simple proof was given by Bertozzi and Constantine. That's the case alpha equals 0. Alpha equals 1 is the analogous problem for the surface quasi-geostrophic equation, which is some equation that is supposed to be supposed to capture some of the many features of how weather evolves in the Earth's atmosphere. So I don't have time to explain much, but we look at the domain omega at time 0. We suppose that it has a smooth boundary, and we ask how it evolves, and can a singularity form in finite time? It's known. It's Jose Rodrigo's thesis with further results by Gancedo. It's known that omega, that the region stays smooth for a short time, but it's believed that a singularity forms in finite time. And at least for this parameter alpha greater than 2/3, there's convincing numerical evidence. And here's what happens. At time 0, you have the green region, which may look as if it has corners, but they're an artifact. That's supposed to be a smooth region on the left. In the center, you can see that the two tips are sharpening and approaching each other, and at some limiting time, the tips touch each other, and also become the curvature blows up so that in a neighborhood of that dot, the region has 4 arcs. Okay. And so that's what numerical evidence indicates, and moreover, that breakdown appears to be appears to be asymptotically self-similar, and all right. Furthermore, more recently, there is another numerical simulation, this one of Scott and Dritchell in a phys revlet, which shows the following very strange behavior. So let me see if I can quickly go through this. Here is a region, not shown very much magnified, but sort of 2 blobs connected by a thin filament. Now, if you look at this little tan square in the thin filament and blow it up, you get the bigger tan square, in which you see here's part of a blob and here's part of a blob, but sitting in there is the green square. And if you blow up the green square, you can see the end of a blob, and there's maybe the beginning of the next blob, but in there is the purple square. And if you blow that up, you have this sort of light blue, bluish gray, whatever square, and you blow that up and it looks like this. And if you blow up this revolting shade of green, you get that. And if you then blow up the lilac, you get that. And finally, if you blow that up, you get that. And so it appears that there is a self-similar cascade of wiggles. And nobody understands that at all. All right, so those are phenomena that seem to happen this is for the case, this is for the SQG equation. All right, so nobody understands that, but there's convincing evidence, and there is a scenario, as opposed to, let's say, for 3D Euler, where there's evidence that's suggestive but not 100% convincing, and it's very far from clear what's going on in the scenario. All right, let me sketch the proof of something. So I have about 15 minutes. Maybe I'll take a little less, God willing. So I'm not going to talk about any more about alpha patches because we don't have any proof at all. I'm not going to talk about water waves because of time limitation. I'm going to pick out the Muskat problem and explain how we prove that the breakdown occurs the way I said. Okay, and I don't promise that the details are right, but you don't care. If you do care, you can look at the paper. Okay, so here are the main steps. First of all, we're going to distill all of the equations for the Muskat equation for the Muskat problem into one contour equation. Okay, so there's going to be an equation for an evolving contour. We will then find a real analytic solution to that contour equation that turns over. Remember, what we want is something that turns over and then forms a singularity. First, we will find something that turns over but does not form a singularity. Then we will pick the correct norm, and picking the correct norm is a very significant part of the trickiness of the problem. Once we have picked the correct norm, we will take our solution that turns over but does not become singular, and we will perturb it in the correct norm in order to obtain a Muskat solution that turns over and breaks down. That's the plan from 50,000 feet. Okay? Okay, now writing down the contour equation. If you look at the problem, if you apply elementary potential theory, the Biot-Savart law, whatever, and if you make one integration by parts, that's all it takes to write down a contour equation. And so here it comes in just a minute. Notice that the z of alpha t is a point in the plane, so it has two components, z1 of alpha t and z2 of alpha t. Okay, and now there's the Muskat equation. That integral equation is equivalent to the Muskat equation. Well, it's equivalent to the Muskat equation for one particular choice of parametrization of the curve. Okay? So we're trying to solve that equation.
How do we remove singularity in the equation?
I'm sorry?
How do we remove singularity in the equation?
Ooh, to remove the singularity. It's a bad denominator. How to describe? Oh God. I will. Let's forget it for now. This should be a pleasant after lunch talk. I would be delighted to tell you more than you would be delighted to hear later. Okay. Okay. No. Okay. Thank you for your interest. Okay. So that's the equation. Okay. Now the first thing we have to do is to find a real analytic solution that turns over. So let's look at what happens at the exact moment of turnover. So at the exact moment of turnover, the curve z, let's say z0 of alpha, that's our real analytic turnover solution, is going to have a vertical tangent someplace. Let's say it has a vertical tangent at the origin. Now, if our curve is real analytic, then there is a solution for short time, and it remains analytic for a short time because morally, although this is non-local and nonlinear and it looks truly disgusting, morally it is a first-order problem. And so Cauchy-Kovalevsky applies, some version of Cauchy-Kovalevsky applies, and so there is a real analytic solution. Now the tangent is vertical at time 0, but at small non-zero time, the tangent will not be vertical. And the crucial question is, I forgot to say, it's convenient to take the initial data to be an odd function of alpha, because then if you look at the equation, the z0 of alpha t will continue to be an odd function of alpha for all t, and therefore, in particular, the origin will always sit on the curve. That's convenient. Okay, so since the origin sits on the curve, we can then ask, how about this angle? What is it doing as a function of time? Now, I would like to adopt the convention that in this picture, the angle theta of t is negative. And if instead the tangent were like that, as I'm trying to draw with the laser pointer, then the theta of t would be positive. So we want to look at that angle. And the crucial question is how it's changing with time. And in particular, the key question is, look at the rate of change of that angle at time 0. Okay? If it's positive, that's the good case, and that's a turnover. So then at small negative time, theta is negative, and so the picture is like this. At time 0, we took our initial condition to have a vertical tangent, so theta is 0. And then at positive time, theta is strictly positive, which means that the curve has turned over. So we get a turnover if the rate of change of the angle at time 0 is positive. On the other hand, if it's negative, the situation is the opposite. For small negative time, the thing has turned over already for some reason that it's not clear. We don't know what happened back there. But this thing has turned over. At time 0, we have the vertical tangent, and for positive time, as we go forward, the turnover is removed. So from our present point of view, in which we're trying to produce a turnover, negative d theta by dt is bad, positive d theta by dt is good. And so, look at the formula for d theta by dt at 0. There's some disgusting formula that you can write down. And you can ask, is it forced to be positive? Is it forced to be negative? Or can it have either sign? And it's a mess, but the fact is that it can have either sign. And And so therefore, in particular, by simply picking the correct z0 of alpha at time 0, we can create a turnover. Okay? So what have we done? We've made our unperturbed solution z0. There it is. And it satisfies the Muskat equation in some short time interval centered at time 0. And it has an analytic continuation to a strip for each t in negative, from minus t0 to plus t0, because we're in the Cauchy-Kovalevsky world. Okay? So this is not merely a solution, it's an analytic solution. T is a real number in this time interval, but alpha is to be thought of as a complex number in a strip. And this solution, moreover, turns over at time 0. That's what we've got. Okay? Now comes the joy of trying to perturb that in such a way that it turns over. So the plan is now, remember we were supposed to pick the correct norm. In fact, we're picking the correct family of norms. For each time in that interval from minus t0 to plus t0, we're going to define a norm on pairs of functions z1, z2. We're going to look for a Muskat solution z that is close to z0 of alpha t in the above family of norms. That means for each t, for each fixed t, if I look at z of alpha t, for that fixed t, that's close to z0 of alpha t for the same fixed t in the norm corresponding to that t. But we're going to obtain z from z0 by perturbing it slightly in such a way that the perturbation z is c3 but not c4 in any neighborhood of alpha equals 0. So in some norm or other, z is close to z0. However, z0 is real analytic, and yet z is not c4. So what kind of a norm will do that? Well, you'll see in a minute, or in a couple of minutes. And the solution z is still defined here in the same time interval as before. It turns over because it's close to z0, which turned over, and it breaks down because we declared that it breaks down. Okay? So the goal is to do that. Now, how are we going to do that? Well, to define the norms, I'm first going to introduce a family of domains in the complex plane parametrized by time. Each of these domains, omega of t, will contain the real axis. Okay? At time t equals plus t0, the moment of breakdown, the domain pinches off to 0 thickness at one point. So here's a picture of the domains, not to be taken too seriously. But at the beginning of our time interval, t equals negative t0, here's the point alpha equals 0 where the interesting stuff happens. Our region in the complex plane looks like this. But by the time we get from here to here, the region is starting to pinch off. It's getting thinner near alpha equals 0, and whereas it's getting fatter over there and over there. And for the first time, at time plus t0, the thickness is 0 at that one point, but it's gotten rather fat here and here. Okay, so these are our time-varying domains. The domains have to be picked very carefully to reflect the behavior of the unperturbed Muskat solution, z0, in a way that I don't have time to describe. Okay, but the behavior of the unperturbed Muskat solution, the real analytic one, influences how you choose the domains. Note that our domains are sets of complex parameter values alpha. They are not sets of physical points. Okay? And now what is the norm? Well, here's the family of norms. Given a time t, x of t denotes the space of continuous functions capital F from the closure of that time-varying domain omega of t into C2 because remember we want two components, z1 of alpha t and z2 of alpha t. Okay. F is analytic on omega of t, it's continuous on the closure, and furthermore, its restriction to the boundary belongs to the Sobolev space H4 of the boundary. Why H4? Because if you take that awful equation, I guess this is approximately, this is something like an answer to the question you asked before. How do you make any sense out of such an awful equation? Given any equation, almost any equation, if you differentiate it enough times, it looks linear. And if you differentiate the Muskat equation 4 times, it looks linear. Okay, and so we use the H4 norm. And so X is the space of all those, and we set the norm of F in the space H of X, as at the bottom of the slide, to be the H4 norm of the restriction of the analytic function F to the boundary of the time-varying region omega of t for each fixed t. Okay? Those are our norms. Okay, so now now that we have the family of norms, we would like to perturb the Muskat solution. And so what we want is a solution z of alpha t without a 0. It's defined in the same time interval as before, negative t0 to plus t0, with the properties indicated on the slide. First of all, if you look at z of t minus z0 of t, that has small norm in the space x of t for each t from negative t0 to plus t0, where z0 is our unperturbed solution. Furthermore, z of t0 is prescribed and close to the unperturbed fellow. So the way we obtain z is that we start at the end of time, t plus t0, and we solve backwards. So we take a small perturbation of z0 in this norm, and we solve backwards in time, hoping that our solution will exist for all times in here and remain close to z0 in the norm x of t. That's the plan. Okay, now this can be carried out because we can prove an energy inequality. There it is near the top of the slide. Notice we have minus d by dt of the norm squared of a difference. That minus sign is good because we're solving for time running backwards. And so by a simple Grunwald inequality, one understands that if z starts out very close to z0 at t equals plus t0, then when we solve backwards throughout the whole time interval, the solution exists and it remains close to z0. That's fine if you can prove the energy estimate, but if you look at the end, when you try to prove the energy estimate, there are uncontrolled terms that could be much bigger than, so big that they have the potential to ruin everything, but you can control their sign if you carefully pick the family of domains to reflect the behavior of the unperturbed solution. Okay? And that's a long story that we are definitely not going to discuss. Okay. So once you believe that, we're in the following situation. We may prescribe the z of t of t0 in the space x of t0. It's anything you like, provided it's sufficiently close to the z0 at t0 in the space x of t0. X of t0 is a space of analytic functions on a domain that pinches off at a point. Functions in that space need not be real analytic or even C4 in a neighborhood of alpha equals 0. They're H4 but not C4. And so when you pick such an initial thing in such a way that when you restrict it to the real axis, it is C3 but not C4 in any neighborhood of alpha equals 0. And so we have found a perturbed Muskat solution that turns over and at time plus T0 no longer belongs to C4. If you think about what just happened, this Muskat solution is real analytic absolutely everywhere except at the last time T0 and at the one point alpha equals 0. Everywhere else it is real analytic by the nature of these spaces x of t and by the way we constructed our solution. So that's the sketch of the proof that the Muskat equation breaks down. Thank you.
Questions, remarks?
Just some curiosity about this Muskat problem.
Okay.
Of this overdamped fluid motion. So I guess, if you have just a regular Euler equation, you get in the linear case, you have Kelvin-Helmholtz instability.
Yes.
Situation like this. What is the situation in the Muskat equation? You have also similar
Well,
sort of
so if you linearize about, let's say, about a flat solution,
yeah,
then
if you have a discontinuous or also some sort of a profile like this, which can be also with finite distance. Do you get those instabilities? Or
Wait. So what is the question again? Just say.
if it's linearly unstable, and under which conditions it is?
Oh, it is linearly unstable if locally anywhere on the interface the heavier fluid lies above the lighter fluid.
Otherwise, no.
Otherwise, if everywhere the heavier fluid is locally underneath,
Yeah.
then it is linearly stable.
Even if there is a velocity jump between upper and lower interface, like in the Kelvin.
Yes.
So it's different.
It is different. It is different. Sure. It's the difference between F equals ma and Darcy's law. Yeah, of course. Sure.
You don't have inertia. You have too much inertia.
Right. Okay.
In those alpha patches, where were you getting the self-similar wiggles?
Where? All right, from Dritchell and Scott, who got them from some numerical simulation.
But what's the actual configuration that leads to that?
All I can do is refer you back to their paper. I emailed, I was naive, I asked them, wow, I said, what a wonderful thing. Oh, thank you very much. Could we see your code? Oh, of course. Well, okay, great, could you please send it? No code. I gather that this is not an unusual situation. So, I mean, if you like, I can zip back to the slide with the reference to, I mean, Dritchell and Scott physical review letters. Do you remember, Javi? Do they specify that? Oh, an ellipse? Oh, thank you. Okay. Thank you.
No, it rolls, like the two dogs roll, and then there is filament that connects one with the other, and that's the picture. There was one on top of that. And from there you can transform.
Okay.
Other questions? Yeah, we mentioned Helle-Shaw, right?
Yes.
It is equivalent to the same.
Yes. So this is another experiment where another physical situation which is apparently governed by the same set of equations. Is there anybody in the audience who knows much more physics than I do and could explain why that's true? No. Okay.
So it is wrong.
I'm sorry?
If nobody can explain, then it's wrong.
Okay.
Okay, very good. So if no more questions.